Class 12, Chapter 5, Continuity and Differentiability, Exercise 5.1, third question. Examine the following function for continuity. So they have given a function, we have to check its continuity. This is sub-question B. The sub-question A and D I have already solved in the previous video. Let us solve. Given function f of x is equal to 1 by x minus 5 and x is not equal to 5. This is a rational function. Why it is called rational function? Because it is polynomial by polynomial. So numerator is a polynomial function, denominator is a polynomial function, and hence we call this as a rational function. But here they have given x is not equal to 5. Why x should not be equal to 5? Like why we should not substitute 5 here? So let us input x equal to 5 and check what is the output we will get. So 1 by x minus 5, let us substitute 5 in the place of x. 1 by 5 minus 5, and we know 5 minus 5 is 0. So 1 by 0 is nothing but undefined. So we will never give divisor equal to 0. This is never accepted. This condition is undefined for us. So that is why we should never give x equal to 5. Other than that, you can give any real number to it. You can give 1.2, square root 2, 1 lakh, 10 crore, any number. But you should never give the value 5, because if you give x equal to 5, you get the answer as undefined. This we will visualize in the graph also. Now what is the domain of the function? Domain of f of x df is equal to the set of all real numbers. You can give any number except which number should not be given as input, that is 5. Now we know the domain of this function, that is what are the allowable inputs. Let C be any arbitrary real number. So C can be any real number in the domain df equal to all the real numbers except 5. Then this function is continuous, then f is continuous in the domain df if, so when it is continuous, when limit x approaches c, f of x is equal to f of c. So when the limit value is equal to functional value, then we say that this function is continuous. So in my previous video, I have explained about the limit value and the functional value. Okay, if this condition satisfies, then we say that the function is continuous. So first we will check for LHS, then we'll check for RHS. We'll check if both are equal. If they are equal, they are continuous. Okay. Let us label this as 1. Now, LHS of 1. Let us take the LHS of 1. Limit x approaches c, f of x is equal to limit x approaches c. So how the function has been defined? 1 by x minus 5 and x is not equal to 5. Now this is equal to, so this is polynomial by polynomial function, and we can substitute the value of c in the place of x. So directly we can write 1 divided by c minus 5, but even c should not be equal to 5. Right? So this is the LHS. So we got LHS as 1 by c minus 5. Let us write it as 2. Now we'll take RHS of 1. Let's take RHS of 1. So to solve this function, see, this is similar to f of c, f of x. Just in the place of x, we have to give input as c. So in order to get this is the function that we have to use. So f of x is equal to 1 by x minus 5. So x is not equal to 5. If you substitute c in the place of x, that is f of c. So this implies f of c is equals to 1 by c minus 5. So c is not equal to 5. Let us label this as true. Now this 2 and 3 are equal, right? This is also 1 by c minus 5. This is 1 by c minus 5. So here this we got 1 by c minus 5. This is also 1 by c minus 5. So what we can write? Since LHS is equal to RHS, therefore limit x approaches c, f of x is equal to, so what is the value we got here is 1 by c minus 5. C is not equal to 5. And this is equal to, this is in turn equal to f of c. So LHS is equal to RHS. Hence, the given function f of x is equal to 1 by x minus 5, where x is not equal to 5, is continuous in the domain df is equal to all the real numbers except 5. Now let us visualize this rational function in the graph. So this part is called as the domain of the function, which is the x-axis, and this is the y-axis from where you get the outputs, that is f of x. Now in the domain, we have already written that we can take any real number except 5. So we can take any real number except 5. Since we cannot take this number because we will get undefined, we will draw a straight line, that vertical line, which is called as vertical asymptote. So if you see this vertical asymptote in any graph, it is understood that the function is not defined at this point. This input cannot be given to this function. Now, we have written let c be any arbitrary real number. So in the x-axis in this domain, c can be any number. It can be minus 1000, minus 6, minus 5.7235, or any number except 5. Except 5. It can be even 5.00001, but not 5. And you can give any real number. It extends both the directions. It extends in both the directions. Okay. Now let us select c is equal to 4. Okay. And we will see whether this function is continuous at this particular point. Algebraically, we proved that this function is continuous, but let us prove the continuity using graph. Now c is equal to 4. Now to prove that the limit exists, let us say that we are traveling towards c is equal to 4 from the left hand side. So if you observe the graph of the function, it is approaching towards one point, that is minus 1. So if you approach 4 from the left, the graph of the function is approaching towards minus 1, that we get from the y-axis. Now we approach 4 from the right side. Then you see that the graph of the function is also approaching towards one number, that is -1, this point. Left side it's approaching -1. You travel from the right side, it is approaching towards -1. So that's why we say limit exists and the value is -1. To get the f of c value, that is the functional value, 1 by x minus 5, in the place of x we have taken 4 here, the input 4 we have taken. So 1 divided by 4 minus 5 is -1 and 1 by -1 is -1. So here left side is equal to right hand side. Therefore we say that this function is continuous at this point. We have selected c is equal to 4 and we have proved that at this point it is continuous, and it's the same case for any real number c that you select at this point except 5.